Alright, hello. Got a follow-up video here, looking at continuity still, and kind of continuing where we left off. Going to see some things, some ways we can use this important property, and one is with the limit computation, and then introduce to you a result called the Intermediate Value Theorem. We won't do a ton with it, but it's a really nice, important result. We'll say one or two things, I guess. Okay. So just as a reminder, when we define continuity, we use limits in that definition. But with this new class of continuous functions that we know, polynomials, rational, so polynomials, rational functions, exponential, root functions, etc. And then the kicker, combinations of these functions. So let's say plus, minus, times, division, composition, etc. So writing it all out just so we're sure we remind ourselves. All of a sudden we know of a ton of functions that are continuous and where they're defined. And so we can use the fact they're continuous to kind of switch roles and actually evaluate limits there. So it started off, again, we defined continuity in terms of limits, but now if we know something's continuous, we can use that to compute a limit. That turns out to be pretty handy. So quick example, something like this. Now if we were going to do this without continuity properties, this is probably a pretty tricky one to tackle. We'd break it down into, using the limit laws multiple times. So we could use multiple applications of limit laws. And it wouldn't be that bad. Not the end of the world. But instead, we could say this is continuous on its domain. And I won't write everything out because of the space, but let me just ask, why? And you could say, well, I could see this as a product of the 2x times the square root of x squared plus 7. 2x certainly is a continuous function. I feel like it's a polynomial of very basic type, a linear function. And then is this other one continuous? Well, it's a root composed with a polynomial. Polynomial is convergent polynomial is continuous everywhere. And if you take a root function is continuous on its domain. So this is going to be continuous on its domain, which, as it turns out, is all x values because this is never negative, which was the potential problem. So it's continuous on its domain, which is all real numbers in this case. So no restrictions. It's continuous everywhere. So that limit I can just do a direct evaluation. And so I get 2 times 3, we'll call it 6, times the square root of 9 plus 7, which is 16. Square root of 16 is 4. And so that limit, the limit of that wacky expression there as x goes to 3 is 24. We could do it, it wouldn't take a ton more time to use the limit laws, but it is faster using the continuity property. So we want to use the continuity to help evaluate limits. And there are a ton of problems that you can work on doing this, and that's going to be a big part of homework and practice and things like that from this section, but I'm not going to do any more on these slides. The other thing I wanted to mention was the Intermediate Value Theorem. And so for the setup here, let's just say start by considering the graph, whatever it is we've got here. So I've got my kind of coordinate plane here. Looks like I've got a function f. I don't know too much about it. At A, there's the function value. At B, there's the function value. And I've got this red dotted line here. And what this is saying is that if f is continuous on this interval from A to B, there's no way that I can get from here to here without crossing over that dotted line. There's just no way. I can avoid it as long as I want, but eventually I've got to cross over it. Maybe I cross over it a bunch of times. That's okay. But what the theorem is going to tell me is that basically all these intermediate values in between the function values here, they're all achieved in at least one point in between A and B there. So thinking of it kind of visually is a useful way, I think, for trying to make sense of it. So here, the idea behind the Intermediate Value Theorem, we use this for the abbreviation, is that if f is continuous, we can't sketch the graph of that function without crossing the dotted line. We have to cross it. So the function takes on all intermediate values, and that's where that word comes from. You know, sometimes in math and other things, you get something named after a person, and it doesn't tell you anything about what the result tells you. But here, the name of the result tells you. I mean, intermediate values, taking on all the intermediate values in between there. Here's a formal statement. So suppose f is continuous on closed interval a to b with n a value between f of a and f of b. So if we like, we can jump back. You can imagine, you could say this was n. Assuming that the f of a does not equal f of b. It has to be something in between them. So the result says that the theorem says that there exists a number between a and b such that f of c equals n. So there's something in between a and b such that that function value is exactly n. There might be more than one. This is just saying that there exists. There might be multiples. There's a number of applications. There are a number of places this is useful. For us, we kind of just want to be familiar with the statement. The one application that we do explore just a little bit would be a cool way of using this would be to find roots of equations. For example, showing that there is a real root to this equation. Now you might say, if I say some function f, let's say f of x equals that. Well, I know the behavior. I know the end behavior. I know that, you know, for large x values it's going off this way. For large negative x values it's going off this way. So somewhere in between it's going to cross over. But here's the kicker. We're saying we want to show that there's a real root between 1 and 2. That's a little bit trickier. You know that this has at least one real root, but we're not quite sure where it is. So let me clear up this space a little bit. So let's see how we can do this using the intermediate value theorem. So I'm going to let f of x be this big mess right here. I don't know why I'm writing it up here. Alright, so let's note f of 1 equals 1 minus 1 plus 3 minus 5. I think that's negative 2. Double check that. F of 2 is, 2 to the 5th. I just happen to remember that's 32. Minus 2 cubed is 8. Plus 3 times 2 is 6. Minus 5. Oh boy. So it looks like that is 24 plus 6 is 30 minus 5. I think it's 25. Certainly seems to be positive. So here's the idea. This is negative. This guy's positive. So notice that in between, or 0 is between f of 1 and f of 2. Now, f is continuous on the closed interval 1 to 2, but it's continuous actually everywhere. That's just going to get a little crowded, so I'll leave that out. But it's continuous on that interval because it's polynomial. Maybe I'll write it right here. So continuous everywhere, in particular that closed interval. That means there is a c between, so some number in that interval, such that f of c equals 0 by the intermediate value theorem. So what we showed, we know that this function is continuous, right? At 1, it's negative. At 2, the function is positive. Since it's continuous, somewhere in between 1 and 2, it has to be 0, because 0 is between a negative number and a positive number, so in particular between negative 2 and positive 25. So it has to hit that value at some point, maybe multiple times, but at least at one point, for some number in between those inputs, 1 and 2. All right. So there's kind of a neat application. You know, how much good does it do us practically speaking? I don't know. Maybe it's not a super real-world application like figuring out the force due to some mass that we're pulling out of a well or something. I don't know, but it is a neat application of the result. So want to keep that result in mind. It's the very end of the topic, but just understanding continuity, the definition, and how to use it for computing limits is probably the bigger task. But do keep this result in mind. It's a neat one.